strap in. The countdown to Mars has started, and the engineers running the numbers know something the brochures don't say. The first crew to touch red dust will never feel Earth again. You'll see the launch window that opens once every 2 years, the fuel math that breaks every return plan, the radiation dose that ends careers before the ship even lands, a rocket that has to be built on another planet by people whose hearts are already shrinking. If this kind of mission planning grips you, hit subscribe and stay aboard. We've got 33 waypoints between here and the truth. Strap in. We launch now. Picture mission control on a Tuesday in July. The clock isn't counting down to a launch, it's counting down to a planet. Mars and Earth are racing around the star at different speeds. Earth completes a lap every 365 days. Mars takes 687. They only line up in the right geometry for a transfer once every 26 months. Miss that window by a week, and the next chance is 2 years and 2 months away. There is no rescheduling. There is no flexibility. The planets don't wait. This is the first wall that engineers slam into when planning a Mars mission, and it shapes everything that follows. A launch window for Mars isn't just a date, it's a narrow tunnel in space and time, maybe 3 weeks wide. Inside that tunnel, a spacecraft can leave Earth on a curved path that intersects where Mars will be 6 to 9 months later. Outside that tunnel, the math collapses. Fuel demands go vertical. Trip times double. Crews die before arrival. Mission planners call this the synodic period. The crew calls it the cage. Here's what makes it brutal. If you launch a crew toward Mars in this window, you are also locking in their return window before they leave. Because Earth and Mars need to line up again for the trip home. And by the time the crew lands, walks the surface and sets up base, that return alignment is already more than a year away. The home and transfer orbit, the cheapest path between 2 planets, demands you wait. It demands the crew sits on Mars until the geometry returns. Skip that wait, and the fuel cost to push against the orbital math becomes impossible. Not difficult. Impossible with chemical rockets. So, the first decision a Mars mission makes is also the last. Once the crew launches, the calendar is locked. 21 months minimum, round trip. Often longer. And every day of that calendar, 100 things can fail. NASA has studied dozens of mission profiles. Every single one bends to the launch window. Robert Zubrin's Mars Direct plan accepts a 500-day surface stay. The design reference architecture from NASA accepts 540. SpaceX's Starship plan accepts 26 months total. They all bow to the same orbital mechanics. Because no one has built a propulsion system that doesn't. Imagine being the crew commander. You strap into your seat in 2033. You know the next time you might breathe Earth air is 2036. You know the universe doesn't care about your wedding anniversary or your father's funeral. The window opens. You go. Or you stay forever. And here's the part that gets darker. Engineers have been studying these windows for over 50 years. The Soviets planned their first crewed Mars attempt for 1971. Wernher von Braun mapped a manned Mars launch for 1981. Every plan since has shifted by decades, but the windows haven't. Mars is still on its same lap around the star, indifferent. The first humans who launch will be doing it because the planets finally agreed. But agreement isn't safety. The window only buys you a ticket out. It says nothing about whether physics will let you come back. And when you study the curve that ticket actually flies, you find something that should have stopped this mission decades ago. The path from Earth to Mars isn't a straight line. Straight lines don't exist in space travel. What the crew flies is a curve, and that curve has a name. The Hohmann transfer. Walter Hohmann figured it out in 1925, working in his apartment in Essen, Germany, on a problem nobody was paying him to solve. He showed that the most fuel-efficient way to move between 2 orbits is an ellipse that touches both. One end of the ellipse kisses Earth's orbit, the other end kisses Mars's. The spacecraft falls along that curve, coasting most of the way, burning engines only at the start and the end. It is elegant. It is cheap. It is also a trap. Because that curve takes between 6 and 9 months to fly, and the crew flying it has no exits, no off-ramps, no rest stops. Once the engines shut down after the first burn, the spacecraft is a thrown stone. Gravity decides where it lands. The crew watches Earth shrink behind them and Mars grow ahead, and there is no decision left to make for half a year. That's the Hohmann curve on the way out. Now picture the return. When the crew finally arrives at Mars, Earth has moved. By the time they land, set up, and complete their surface mission, Earth is on the wrong side of the star. To fly the cheap Hohmann curve home, they have to wait until Earth swings back into the right position. That wait is roughly 500 days on the surface, sealed inside whatever shelter they can build, while their bodies break down and their food supply gets counted by the gram. Then the return curve itself adds another 6 to 9 months. Total round trip on a minimum energy Hohmann profile, about 21 months minimum, often closer to 30. Engineers have tried to escape this curve for decades. They've designed nuclear thermal engines that could shave months off the transit. They've sketched plasma drives, fusion concepts, antimatter propulsion. None of it has flown. None of it has been tested at the scale needed. The chemical rockets that exist today, the kerosene and methane and hydrogen burners, they cannot beat Hohmann's math. They are the math. Faster trajectories exist on paper. They're called high-energy transfers. But faster means more fuel. More fuel means more launch mass. More launch mass means bigger rockets, and bigger rockets mean costs that even SpaceX cannot absorb. The curve isn't just a path, it's a budget. There's something called a free return trajectory, where the spacecraft swings around Mars and comes home automatically if the landing aborts. Apollo 13 used a version of it around the Moon. Mars free return takes about 2 years total, and the crew never lands. They just look at Mars through a window and fly past. Inspiration Mars proposed exactly this in 2013. They abandoned the plan when they realised no shielding could protect a crew from radiation that long. So the curve dictates the calendar dictates the supplies dictate the crew size, and the crew size dictates how much fuel you need to launch. Which is where the next wall appears, because if you decide you want to come home, the math doesn't just get harder, it gets absurd. The crew has landed on Mars. Day 1. The dust settles, the engines cool, and someone in mission control asks the question every reporter will eventually ask: can we bring them home early? The answer is no, and the reason isn't political or financial or logistical. The reason is the star at the centre of our solar system pulling on everything that orbits it. To leave Mars and reach Earth, you need to throw the spacecraft along a curve that intersects where Earth will be when you arrive. That curve requires Earth to be in a specific position relative to Mars at the moment of departure. If Earth isn't there, the curve doesn't close. You burn the fuel, you fly the trajectory, and you arrive at empty space where Earth used to be 6 months ago. This isn't a software problem, it's geometry. And no amount of money fixes geometry. Now you can fight the geometry. You can burn extra fuel to reshape the curve, to take a faster, hotter, more violent path that catches Earth before it moves. This is called a high-energy return. The cost is staggering. A Hohmann return from Mars uses roughly 4.1 kilometers per second of velocity change. A return that gets the crew home in 3 months instead of 9? That number jumps to over 10 kilometers per second. In rocket equation terms, every additional kilometer per second of delta V multiplies the fuel mass exponentially. 10 kilometers per second on chemical engines means a return rocket on Mars that weighs more than the entire Apollo program. That fuel doesn't exist on Mars. It would have to be brought from Earth. Bringing it from Earth means launching it across 140 million miles, landing it on Mars, and stockpiling it for a year while the crew works. The launch mass to deliver that fuel from Earth balloons to thousands of tons. No rocket on the drawing board can lift that. So the dream of an emergency return dies on the launch pad. Mission planners have wargamed every alternative. What if the crew gets sick? What if there's a fire? What if a meteor punches the habitat? In every scenario, the answer comes back the same. They wait for the window, or they don't come home. NASA calls this characteristic of Mars missions the long abort. On the way to Mars, if something fails, you might be able to swing around Mars and free return to Earth, taking close to 2 years. After landing, abort options drop to 0. You are committed to the surface until orbital geometry releases you. The Soviet space program studied this in the 1960s. Their conclusion, buried in classified reports for decades, was that any crewed Mars mission was effectively a one-way mission unless every system worked perfectly for 3 years straight. They never flew it. The Americans reached the same conclusion. NASA's internal risk assessments for Mars design reference architecture put the loss of crew probability at 1 in 3 for the first mission. That's not a small risk you accept. That's coin flip territory with one bad outcome. And yet the missions are being planned, the crews are being recruited, the hardware is being built, because if the geometry can't be cheated, maybe the fuel can be made on the ground when you get there. That idea has its own problem. A reactor that has never been turned on outside a laboratory. A rocket leaving Earth for Mars has to carry every gram of fuel it will ever burn. There is no gas station between the planets. Whatever you don't bring, you don't get. This sounds simple. It is the most expensive sentence in aerospace. The rocket equation, written by Konstantin Tsiolkovsky in 1903, says something brutal about space travel. To go faster, you need more fuel, but more fuel weighs more, which means you need more fuel to push that extra fuel. The relationship isn't linear, it's exponential. Every additional kilometre per second of speed roughly doubles the fuel you need. For a Mars mission, the speeds add up fast. You need delta V to leave Earth's gravity, more to slip into the transfer orbit, more to brake at Mars, more to land. And if you want to come home, you need delta V to launch off Mars, slip into a return orbit, and brake at Earth. The numbers stack. Total round-trip delta V for a Mars mission, somewhere between 15 and 20 kilometers per second, depending on the profile. For comparison, Apollo's round trip to the Moon needed about 14. Mars is a different beast. Now run the rocket equation backward. For every ton of payload you want to land on Mars and bring back, you need roughly 10 to 12 tons of fuel sitting on the launch pad on Earth. Land 50 tons on Mars for a crewed mission, and you're staring at over 500 tons of fuel and rocket structure leaving Earth. That's why the rockets being built for Mars are giants. SpaceX's Starship, fully fueled, weighs about 5,000 tons on the pad. Most of that is propellant. Here's where it gets worse. If the crew also needs to bring return fuel, the numbers double again, because that return fuel has to be carried out to Mars, decelerated, landed on the surface, and stored for a year and a half before it gets used. Every ton of return fuel landed on Mars requires another ton of fuel to land it, and another ton to decelerate that one. The mass cascade is merciless. Engineers ran the numbers in the 1990s and realized the original NASA Mars plan, the 90-day study, was demanding rockets bigger than anything in human history. The price tag was over $450 billion. Congress saw the number and killed the plan. Robert Zubrin, an aerospace engineer at Lockheed, looked at the same problem and asked a different question. What if you didn't bring the return fuel? What if you made it on Mars? His answer became Mars Direct. The idea was to land an empty fuel tank on Mars first, before any humans, with a small reactor that could pull carbon dioxide out of the Martian air and combine it with hydrogen brought from Earth to make methane and oxygen. Rocket fuel, manufactured on another planet, waiting for a crew that hadn't launched yet. The math worked beautifully. The mission mass dropped by a factor of 3. The price tag dropped with it. NASA studied the plan and integrated parts of it into every Mars architecture since. There is one detail that keeps everyone awake. The reactor that makes the fuel has never been built at the size needed. It has never been tested in Martian conditions. It has never run for the 500 days the crew's lives depend on. And it has to work the first time, on a planet where nobody can fix it. Elon Musk's plan for Mars is the most aggressive ever proposed by a private company. It rests on a single technology that has never operated outside a research laboratory. The plan goes like this. A Starship, the largest rocket ever built, launches from Earth carrying 100 tons of cargo. It lands on Mars. Inside that cargo is a propellant production plant. The plant runs for 2 years on solar or nuclear power, pulling carbon dioxide from the thin Martian atmosphere and water from underground ice. It combines them through a chemical process and produces liquid methane and liquid oxygen. The Starship's tanks are slowly refilled. When the launch window opens, the same Starship that delivered the plant lifts off Mars, accelerates onto a return curve, and brings the crew home. On paper, it works. In practice, almost every step is unproven. Start with the carbon dioxide collection. The Martian atmosphere is 1% the density of Earth's. To gather enough carbon dioxide to fuel a Starship-sized vehicle, you need industrial compressors running continuously for over a year. NASA built a small version called MOXIE and flew it to Mars on the Perseverance rover in 2020. MOXIE produced about 12 grams of oxygen per hour at peak performance. A Starship needs roughly 1,000 tons of oxygen for a single return. That's 80 million times more output than MOXIE has ever achieved. Scaling up by 80 million is the kind of number engineers don't say out loud. They write it on whiteboards, stare at it, and quietly redesign the whole system. Then there's the water. SpaceX's plan assumes the lander touches down near subsurface ice deposits. Mars has ice confirmed by orbital radar, but near the surface can mean a meter down or 20. Drilling rigs that work on Earth use water-based drilling fluids. On Mars, where the surface temperature drops to negative 80 degrees Fahrenheit, water-based fluids freeze on contact. Dry drilling generates heat that melts the ice you're trying to extract. Every prototype tested in vacuum chambers on Earth has clogged, jammed, or stalled within hours. The Sabatier reactor itself, the heart of the fuel production, is a known technology. NASA uses Sabatier reactors on the International Space Station to recycle carbon dioxide. They are reliable at small scales, with continuous human maintenance. Scaling to Mars mission size means a reactor running unattended on a different planet for 18 months, fed by collected gases that may contain dust contaminants nobody has fully characterized. Power is another wall. Producing methane and oxygen at the rate Starship needs requires somewhere between 100 and 300 kilowatts of continuous power. Solar panels on Mars deliver less than half the energy they would on Earth, and Martian dust storms can blot out the panels for weeks. Nuclear reactors small enough to land on Mars exist only in concept. NASA's Killer Power project tested a 1 kilowatt prototype in 2018. The Mars plan needs 100 to 300 of them, so when SpaceX announces a 2028 or 2030 crewed Mars launch, those dates assume every one of these systems works the first time. No prior orbital test of the fuel plant, no surface trial run of the drills, no backup if the Sabatier reactor fails. The crew lands, they turn on the machine, they wait. If the machine doesn't work, they don't come home. And the simplest part of that machine, the part that turns Martian air into rocket fuel, has its own quiet history of failures. The chemistry is over a century old. A French chemist named Paul Sabatier discovered it in 1897 and won a Nobel Prize for it. Take carbon dioxide, add hydrogen, run them through a heated nickel catalyst. Out comes methane and water. The reaction is simple. 4 hydrogen atoms plus 1 carbon dioxide molecule heated to about 300 degrees Celsius become one methane molecule and two water molecules. The methane is rocket fuel. The water can be split into hydrogen and oxygen, where the hydrogen feeds back into the reactor and the oxygen becomes the other half of the propellant. It's a closed loop. It's beautiful. It's also unforgiving. The catalyst inside the reactor, that nickel surface where the molecules meet, has to stay clean. Any contamination poisons it. Sulfur poisons nickel. So does carbon monoxide build up. So does dust. The reactor has to run at a precise temperature window, hot enough to drive the reaction, but not so hot that the catalyst sinters and loses surface area. Pressure has to be maintained. Flow rates have to be balanced. If any variable drifts, the reaction slows or stops, and you don't make fuel that day. On Earth, in a lab, this is manageable. Engineers monitor the system, swap out catalysts every few months, clean the lines. On the International Space Station, NASA's Sabatier unit has been running since 2010, processing crew exhalations into water. It works because astronauts maintain it. They replace failed parts. They reboot the system when it crashes. On Mars, none of that maintenance happens. The reactor lands 2 years before the crew arrives. It runs unattended for the full transit, the full surface stay, and the full propellant production cycle. By the time humans are anywhere near it, the machine has been running for 20 to 24 months in conditions no Earth-built Sabatier has ever survived. The Martian atmosphere is mostly carbon dioxide, which is the input the reactor wants, but it also contains argon, nitrogen, and trace amounts of dust at the molecular level. That dust, scientists have learned, contains perchlorates. Perchlorates are oxidizing salts that destroy catalyst surfaces over time. Filtering the dust out of incoming carbon dioxide requires its own subsystem. Filters clog. Clogs reduce flow. Reduced flow means less fuel produced per day. Over 500 days, small efficiency losses compound into large fuel shortfalls. A reactor performing at 90% efficiency for 500 days produces 50% less total fuel than expected, because the losses stack. Then there's hydrogen. The Sabatier reaction needs hydrogen as input, and hydrogen is the lightest element. It leaks through almost everything. Even welded steel tanks lose hydrogen slowly over time. The hydrogen for a Mars fuel plant has to be either brought from Earth, in tanks that will leak across the entire transit, or extracted from Martian water ice, which depends on the drilling and water extraction systems working. If the water system fails, the Sabatier reactor starves. If the reactor starves, no methane. No methane, no return fuel, no return fuel, no return. NASA has run small-scale Sabatier reactors in vacuum chambers simulating Martian conditions. The tests run for hours, sometimes days. They don't run for months, because no funded program has ever needed to. The full duration test of a Mars-scale Sabatier reactor under Martian conditions has never been attempted. The first time anyone runs that test, the crew will already be on their way, and the input that feeds the whole system, the water buried in Martian ice, is harder to reach than the brochures suggest. Mars has water. That part is settled science. Orbital radar from the Mars Reconnaissance Orbiter has mapped vast deposits of subsurface ice, some of it just a few feet beneath the rusty crust. In some regions, the ice makes up more than half the soil by weight. The trouble isn't finding the ice. The trouble is getting it out. Mars is dry on top and frozen underneath. The surface dust is a powder finer than talcum, and it sits over a layer of cemented soil called regolith, and below that, in the right places, is the ice. Sometimes pure water ice, like a buried glacier. Sometimes ice mixed with rock, more like frozen concrete. To turn that ice into water, then into rocket fuel and drinking water and oxygen, you have to extract it. An extraction on Mars breaks every prototype that has been tested. The problem starts with temperature. Mars' surface temperatures average negative 80 degrees Fahrenheit. The ice isn't soft, it isn't slushy. It is harder than most rocks at those temperatures, and it behaves more like granite than like the ice in your freezer. Drill bits designed for Earth ice shatter against it. Drill bits designed for rock generate friction heat, which sublimates the ice into vapour before you can collect it. The vapour escapes into the thin Martian atmosphere and is gone. Engineers have tried thermal extraction. The idea is to heat the ground, melt the ice in place, and pump the liquid water to the surface. On Mars, this fails immediately. Water can't exist as a liquid at normal Martian surface pressure. It either stays solid or skips straight to vapour, the same way dry ice doesn't melt on Earth. To keep the water liquid long enough to pump it, you have to pressurise the entire extraction zone underground, which requires sealing a hole in regolith that does not seal. Another approach is mechanical. Send a rover with a drill, bring up cores of ice-rich soil, and process them in a heated chamber on the surface. This works, in theory, at very small scales. NASA's Phoenix lander in 2008 confirmed water ice in a small trench it dug. But scaling that up from a few grams to the 100 tons needed for a fuel plant means industrial mining. Continuous operation. Tons of regolith processed per day. No mining rig that size has ever been designed for autonomous operation on another planet. There's also the perchlorate problem. Martian soil contains perchlorate salts, sometimes at concentrations of 1% by weight. Perchlorates are toxic to humans, dissolve readily in water, and contaminate everything they touch. Any water extracted from Martian regolith carries perchlorate with it. Cleaning that water requires chemical processing systems that add another layer of failure points. Robert Zubrin proposed a clever workaround. Skip the ice entirely. Use only the carbon dioxide in the Martian atmosphere combined with hydrogen brought from Earth to make methane through the Sabatier process. The water that comes out of the reaction can be electrolyzed for oxygen. No drilling required. The catch is that you have to bring all the hydrogen from Earth. Hydrogen is the lightest element, which means tank volumes are huge. Hydrogen leaks through almost any container. By the time the lander reaches Mars after a 6-month transit, a significant portion of the hydrogen is gone. Every Mars architecture being studied right now picks one of two bets. Drill the ice and accept the engineering nightmare, or bring hydrogen and accept the leak losses. Either way, the crew's lives depend on hardware that has never been tested in the place it has to work. And that's just the equipment. The crew themselves are facing 500 days on the surface, waiting for the planets to align. What that wait does to a human body is the next problem nobody has solved. The crew has landed, the hardware is working, the fuel plant is humming, slowly filling tanks. And now they wait. 500 days. Roughly 16 months. That is the minimum surface stay required by orbital mechanics on the cheap mission profile. They cannot leave early. They cannot leave late. They have to be ready to launch on the day Earth and Mars line up again, or they miss the window and stay another 2 years. 500 days inside a habitat the size of a small RV on a planet with no rescue. Compare that number to the longest continuous human spaceflight ever recorded. Russian cosmonaut Valery Polyakov spent 437 days aboard the Mir space station in 1994 and 1995. He came back alive. He also reported severe psychological strain, sleep disturbances, and struggled to walk for weeks after landing. His mission set the record. The Mars surface stay would break it before the crew even started their return trip. The habitat itself is a problem. To minimize launch mass, every Mars architecture proposes a small living space, often less than 1,000 square feet of usable interior, shared by 4 to 6 crew members. That's roughly the size of a 2-bedroom apartment, except every wall is also a piece of life support equipment, and you cannot open a window. Every system is shared, every conversation is overheard. Every meal is the same recycled food in slightly different combinations. NASA has run analog missions on Earth to study this. The high seas habitat in Hawaii sealed crews inside a small dome on a volcanic slope for up to a year. The crews were carefully selected, professionally trained, and stayed in radio contact with Earth. Several of those missions reported significant interpersonal conflict. One had to be cut short. Another saw crew members refuse to speak to each other for the final weeks. That was on Earth. With evacuation possible. With breathable air outside the door. On Mars, the door doesn't open into rescue. It opens into a thin, freezing atmosphere that will kill you in minutes. The crew is locked in by physics. There is also the question of what to actually do for 500 days. Mission planners load the schedule with science. Geological surveys. Sample collection. Experiments. But humans are not optimized for relentless, repetitive work without natural breaks. On Earth, weekends exist. On Mars, every day is the same shade of red, the same recycled air, the same 5 faces. Sleep is another challenge. The Martian day, called a sol, is 24 hours and 39 minutes long. That extra 39 minutes shifts the crew's circadian rhythm forward every day. Over weeks, their internal clocks drift away from any standard schedule. NASA's analog studies show this drift causes chronic fatigue, mood disorders, and cognitive impairment. Then there's the dust. Every time the crew goes outside in a spacesuit, they bring Martian dust back into the habitat. The dust contains perchlorates, fine silicates, and possibly toxic metals. Filters help. Filters fail. Over 500 days, dust accumulation in air systems becomes a chronic threat to lung health. And underneath all of this is the radiation. The habitat shielding is thin to save mass. Cosmic rays and solar particles pour through it at all hours. The crew's radiation dose climbs steadily for the entire surface stay, on top of the dose they already absorbed during transit. By the time the launch window opens for the return trip, the crew is exhausted, dosed, dust-coated, and physically deconditioned, and the radiation alone may have already pushed them past the line where survival becomes uncertain. The day the crew leaves Earth orbit, they cross a line. That line is the edge of Earth's magnetosphere, the invisible bubble of magnetism that has been deflecting cosmic radiation away from every human ancestor for hundreds of thousands of years. Past that line, the deflection is gone. The crew is in deep space, and the radiation starts hitting them. Every astronaut who has flown to the moon crossed this line briefly. Apollo missions lasted 6 to 12 days. The total radiation dose to the Apollo crews was high but survivable. A Mars mission crosses the same line and stays past it for 21 to 30 months. The math of that exposure is terrifying. 2 main types of radiation threaten a Mars crew: solar particle events, which are bursts of high-energy protons thrown off by the star during solar flares, and galactic cosmic rays, which are atomic nuclei moving at nearly light speed, originating from supernova explosions across the galaxy. The two require completely different protection strategies, and no shielding can fully stop both. NASA's measurements from the Curiosity rover, which carried a radiation detector on its trip to Mars in 2011 and 2012, gave researchers their first direct numbers. A round-trip Mars mission would expose a crew to about 1,000 millisieverts of radiation over the full duration. NASA's career limit for an astronaut, the maximum dose considered acceptable across an entire career, is 600 millisieverts for a 35-year-old male. A single Mars mission delivers nearly twice that career limit. In one trip, translated into health risk, that level of exposure raises lifetime cancer risk by an estimated 5%. For comparison, getting a CT scan delivers about 10 millisieverts. The Mars crew is absorbing the equivalent of 100 CT scans, spread out over 3 years. That number assumes no major solar event. If a large solar flare hits the spacecraft mid-transit, the dose can spike dramatically in a few hours. The crew's only protection is to retreat into a shielded storm shelter inside the spacecraft, surrounded by water tanks, food supplies, or specially designed plastic walls. Even there, peak doses during severe events can reach hundreds of millisieverts in days. The crew has no warning system that gives them more than minutes. The star throws particles at near light speed, and the radiation arrives almost simultaneously with the warning signal. Galactic cosmic rays are worse in a different way. They are too energetic to fully shield against. A wall thick enough to stop them would weigh more than any rocket can lift. They pass through the spacecraft, through the crew, through everything. Each particle that hits a human cell can break DNA strands, kill the cell, or cause a mutation that becomes a cancer years later. What makes galactic cosmic rays especially dangerous is their effect on the brain. Recent studies on mice exposed to similar radiation showed cognitive decline, memory problems, and behavioural changes. The particles damage nerve cells in ways the body cannot repair. For a crew that needs sharp judgment to land on Mars and survive there, brain damage during transit is not just a long-term cancer risk, it's a short-term mission risk. NASA has studied shielding options. Water walls, polyethylene plastic, active magnetic deflection systems. Each has trade-offs. None solves the problem completely. The crew that arrives at Mars has already absorbed more radiation than NASA's lifetime limits allow, and the planet's surface offers less protection than people assume. Galactic cosmic rays are the most penetrating particles in the known universe. They are not photons. They are not electrons. They are atomic nuclei, mostly hydrogen and helium, but including iron, carbon and oxygen, accelerated to nearly the speed of light by ancient supernova explosions. They have been crossing the galaxy for millions of years, and they hit the Mars crew at the rate of several per second per square inch of skin. You cannot stop them with thin metal. You cannot stop them with thick metal. You cannot stop them at all, in any practical sense, with the kinds of shielding a spacecraft can carry. Here is what makes them special. When a galactic cosmic ray hits a wall, it doesn't just bounce off, it smashes into atoms in the shielding and creates a shower of secondary particles. Neutrons, pions, other fragments. Sometimes the shower of secondary particles is more harmful to the crew inside than the original cosmic ray would have been. This is called the spallation problem. Engineers have tested aluminum hulls, the standard material in spacecraft, and discovered that aluminum makes the radiation environment inside slightly worse than no shielding at all. The aluminum atoms break apart on impact and spray fragments into the cabin. The solution, in theory, is to use lighter materials. Hydrogen is the best shield against cosmic rays because hydrogen atoms don't break apart into fragments. Water and polyethylene plastic, both rich in hydrogen, perform better than metal. NASA designs Mars habitats with water tanks built into the walls, doubling as life support and radiation shielding. The catch is mass. To meaningfully reduce cosmic ray dose, you need walls several feet thick of water or plastic. A spacecraft sized for a 4-person Mars crew, fully shielded, would weigh thousands of tons more than current rockets can launch. So engineers compromise. They use thin shielding for routine exposure and a small storm shelter for solar events. The crew accepts the cosmic ray dose because there is no alternative. Active shielding has been studied for decades. The idea is to surround the spacecraft with a powerful magnetic field that deflects charged particles before they hit the hull, the same way Earth's magnetic field protects us. Designs have been proposed using superconducting magnets. The magnets would weigh dozens of tons, require constant cooling to near absolute zero, and consume more power than any current spacecraft can generate. No active shielding system has been flown on any mission. A Mars mission running for 21 months in deep space exposes the crew to roughly 1.8 millisieverts per day from galactic cosmic rays. Over the trip, that's about 1,000 millisieverts total. The crew arrives on Mars with their cellular DNA already damaged in ways that cannot be undone. Mars itself helps a little. The thin atmosphere blocks some radiation. The planet's bulk blocks half the sky. Surface dose rates are about 0.7 millisieverts per day, less than half the deep space rate. But a 500-day surface stay still adds another 350 millisieverts. The total for the full mission climbs past 1900 millisieverts. That number exceeds NASA's 3% excess cancer risk threshold by a wide margin. It violates current radiation limits for any crewed mission. Mission planners know this. They have written internal documents arguing that the limits should be raised, or waived, because the limits make Mars impossible. In other words, the only way to send humans to Mars under current rules is to change the rules. The radiation isn't going anywhere. And the damage isn't only at the cellular level. The crew's bones, muscles, and hearts are also breaking down in ways nobody knows how to prevent. In zero gravity, the human skeleton starts dissolving. Not metaphorically, literally. Calcium leaches out of bones at a rate of about 1 to 2% per month. Over a 6-month transit to Mars, a crew member can lose 10% of their total bone mass. Over the full round trip, including transit out, surface stay and return, the loss can exceed 20%. Bones evolved under gravity. They are constantly being broken down and rebuilt by cells called osteoclasts and osteoblasts, which work together to maintain density. The system is calibrated to the load gravity puts on the skeleton. When gravity disappears, the load disappears, and the breakdown half of the cycle keeps running, while the rebuild half slows down. The skeleton thins. Astronauts on the International Space Station experience this every day. NASA has tracked it for decades. Every long-duration crew member returns to Earth with measurably weaker bones. Recovery takes years. Some bone loss is permanent. Countermeasures exist. Astronauts on the station spend 2.5 hours every day exercising on resistance machines and treadmills, harnessed in place to simulate gravity loads. This routine slows the loss, but does not stop it. Even the best-conditioned crews lose bone density throughout long missions. For Mars, the math gets worse. The transit to Mars takes 6 to 9 months in zero gravity. The surface stay on Mars is in 38% gravity, which loads the skeleton at less than half the Earth standard. Bone density continues to decline on the surface, just more slowly. Then, the return transit puts the crew back in zero gravity for another 6 to 9 months. By the time the crew approaches Earth on the return leg, their bones may have lost 20 to 25% of their original density. Some studies suggest even higher losses for long missions. What does that mean in practical terms? Bones that thin become brittle. They fracture under loads that healthy bones would absorb easily. Hips, spines, and femurs are at the highest risk. A crew member with severely deconditioned bones can break a vertebra simply by sitting down too hard. Now consider the return landing. The spacecraft hits Earth's atmosphere at high speed. Deceleration during re-entry pulls multiple Gs on the crew. They are strapped into seats designed to spread the load, but their skeletons are still absorbing forces equivalent to 2 or 3 times their body weight, briefly. For an Earth-conditioned astronaut, this is uncomfortable but routine. For a Mars-returning crew with degraded bones, it could be catastrophic. Vertebrae could compress and fracture. Hips could break. Femurs could split. The re-entry that brings them home could be the event that kills them. NASA has not solved this problem. The exercise countermeasures are imperfect. Drugs called bisphosphonates, used to treat osteoporosis on Earth, have been tested on astronauts and slow the loss but introduce their own side effects. Artificial gravity, generated by rotating sections of the spacecraft, would prevent bone loss almost entirely. No spacecraft with rotating crew sections has ever been built. The engineering challenges of structural integrity, vibration, and crew movement in a rotating habitat have prevented every concept from leaving the drawing board. So the crew flies without artificial gravity. They exercise, they take supplements, they monitor their bone density with onboard ultrasound. And they hope. The bones are only one system breaking down. Their muscles are doing the same thing, on a faster timeline, with consequences that hit during the most dangerous moments of the mission. Muscles work the same way bones do. They adapt to the loads placed on them. Lift weights, the muscle grows. Sit on the couch for a year, the muscle shrinks. In zero gravity, the load drops to almost nothing, and every major muscle group in the body starts wasting away within days. The decline is fast, astronauts lose up to 20% of their muscle mass in the first 2 weeks of spaceflight if they don't exercise. The legs go first because they're the most gravity dependent. The back, the core, the neck. Even the muscles in the hands and arms shrink, just more slowly. On the International Space Station, crews follow strict exercise routines, resistance machines that mimic weightlifting, treadmills with bungee cord harnesses, exercise bikes. 2.5 hours every day. The routine slows muscle loss but doesn't prevent it. After 6 months in space, station astronauts return weakened, often unable to walk unassisted for hours or days. A Mars crew faces something worse. The transit to Mars is 6 to 9 months in zero gravity. Then they have to land on Mars and immediately start working in 38% gravity. Their first task is donning a spacesuit, which weighs 200 pounds on Earth. Even at Mars gravity, the suit weighs roughly 75 pounds. A crew member with deconditioned legs, climbing out of a lander after 6 months in zero-G, has to stand up under that load and walk. The first crews may not be able to do it. NASA's analog studies suggest that some astronauts returning from long missions cannot stand for the first 24 hours back in gravity. On Earth, ground crews catch them. On Mars, there are no ground crews. There's also the heart. The heart is a muscle. In zero gravity, it doesn't have to pump as hard because blood doesn't pool in the legs the way it does on Earth. Without that workload, the heart shrinks. Studies of long-duration astronauts have measured up to 27% reductions in heart muscle mass after 6-month missions. A smaller heart pumps less blood per beat. When the crew returns to gravity, the heart has to suddenly handle full Earth or Mars loads. Some astronauts experience near-fainting episodes when they first stand up after long missions. Their hearts cannot push enough blood to their brains. For Mars, this matters at 2 critical moments: landing on Mars after 6 months in transit, and re-entry at Earth after 6 months returning. Both events demand cardiovascular performance from a heart that has been quietly atrophying. There's another twist. The shape of the heart changes in zero gravity. A 2014 study found that astronauts' hearts become more spherical, like balloons, instead of the elongated shape they have on Earth. This shape change reduces pumping efficiency. After return, hearts gradually return to normal shape, but the recovery takes months. Eyes have their own problem. Over half of long-duration astronauts develop a condition called spaceflight-associated neuroocular syndrome. Fluid shifts toward the head in zero gravity, increasing pressure inside the skull and pushing on the back of the eye. Vision blurs. Some astronauts return with permanent vision changes. For a crew that needs to read instruments and pilot a lander, deteriorating eyesight mid-mission is a real risk. Every system in the human body that evolved under gravity is breaking down during the transit. The crew that lands on Mars is not the crew that left Earth. And the body that survives the surface stay may not survive what comes next. The return trip is where everything that has been quietly breaking down becomes lethal. The crew has spent 21 months exposed to radiation, microgravity, low gravity, isolation, dust, and dehydration. They've eaten the same recycled food for over 600 days. Their bones are 20% lighter than when they left Earth. Their hearts have shrunk and changed shape. Their muscles, even with constant exercise, have lost a quarter of their mass. Then they have to launch off Mars. The Mars Ascent Vehicle, or MAV, is the rocket that carries them from the surface back to orbit. It has to generate enough thrust to escape Mars gravity, which means the crew experiences several Gs of acceleration during liftoff. For a fresh Earth-launched astronaut, 3 Gs is uncomfortable. For a deconditioned Mars-returning astronaut, 3 Gs may be the load that breaks them. Heart and circulation come first. The crew's smaller, weaker hearts have to maintain blood flow to the brain during high G acceleration. If a heart cannot keep up, the crew loses consciousness. A pilot who blacks out during ascent loses the ability to abort or correct problems. An automated system can fly the rocket, but humans are still in the loop for emergencies. A crew passing in and out of consciousness during launch is at the mercy of pre-programmed systems. Bones come second. The compression forces during liftoff are spread across the spine and pelvis. Vertebrae weakened by 20% bone loss can fracture under sustained acceleration. Hip joints can compress. Even the seats, padded to spread the load, cannot fully protect a skeleton that has been thinning for 2 years. The transit home is another 6 to 9 months in zero gravity. By the time the crew reaches Earth, they have spent close to 30 months total in low or zero gravity. Their bodies have crossed thresholds that no human has ever returned from. The longest single mission any human has completed is Valery Polyakov's 437 days on Mir. He came back to normal Earth gravity. He needed weeks to recover. A Mars crew has spent more time in altered gravity than Polyakov, and they are returning to Earth at high speed through the atmosphere. Re-entry is a violent event. The capsule hits the upper atmosphere at over 25,000 miles per hour. Deceleration peaks at 4 to 7 Gs depending on the trajectory. The crew is strapped in, helmets on, breathing oxygen, and absorbing forces that healthy astronauts find punishing. For a Mars crew with cumulative skeletal damage, re-entry forces could cause crush fractures of the spine. Hip joints could shatter. Sternums could crack. The crew might land alive but be unable to evacuate the capsule on their own. They might land alive but with internal injuries that prove fatal in the hours after splashdown. NASA has studied these scenarios. Internal medical risk assessments for long-duration Mars missions assign significant probability to crew member injury or death during return. The agency has not published full numbers, but the studies acknowledge that no countermeasure currently exists that fully prevents physical degradation over the mission timeline. Some mission concepts now suggest the crew should land on a recovery ship at sea, where medical teams are immediately available. Others propose a slower re-entry profile that spreads deceleration over more time, reducing peak G loads. Both approaches add complexity to a mission that is already operating at the limits of what physics allows. There is another option, and it is the option that several mission architectures quietly accept. The crew never returns. They land on Mars, they stay on Mars, and they are not subjected to the body-breaking violence of a return trip. The numbers, when honestly run, suggest this option may be the only survivable one. Mars pulls on objects with about 38% of Earth's gravitational force. A 200-pound astronaut weighs 76 pounds on the Martian surface. A jump that lifts you a foot on Earth lifts you nearly 3 feet on Mars. Tools feel light. Walking feels strange. Everything is half-loaded. For the first few hours, this seems like a relief. After 6 months in zero gravity, the crew expected Mars to feel heavy. Instead, it feels gentle. The skeleton is loaded again, but only at a third of what it evolved for. This is the trap. A third of normal load is enough to remind the body that gravity exists. It is not enough to rebuild what zero gravity destroyed. Bone density loss continues on Mars, just more slowly. Muscle atrophy continues. The cardiovascular system stays partially deconditioned. Over 500 days on the surface, the crew's bodies do not recover. They keep declining, at a slower rate than during transit, but on the same downward curve. Studies of gravity's effect on human physiology have given researchers reasonable confidence about Earth gravity, which we evolved in, and zero gravity, which we have measured for over 60 years. The effects of partial gravity, between 0 and 1, are almost entirely theoretical. No human has spent more than 3 days at any partial gravity level. Apollo astronauts walked on the moon for hours in 16% gravity and returned. We have no data on what 30 days or 100 days or 500 days at 38% gravity does to the human body. The few experiments done with animals at simulated partial gravity, using centrifuges on the space station, suggest that bone and muscle continue to lose mass, just more slowly than in 0G. Whether human bones can stabilize at some new equilibrium under Mars gravity, or whether they keep losing density indefinitely, is unknown. The crew lands as the experiment. Movement on Mars is also stranger than the brochures suggest. With less gravity, the crew's natural Earth gate does not work. Each step launches them too high, lands them too softly, and throws off their balance. Apollo astronauts on the Moon had to develop a kind of bouncing skip to move efficiently. Mars gravity falls between Earth and lunar values, which means crews have to invent a new way of walking that no human has practiced. Every task that involves balance, lifting, or coordinated movement gets harder. Driving a rover, climbing into an airlock, planting a tool in the regolith. The motions are all subtly off. Then there's the spacesuit. On Mars, a fully equipped suit weighs roughly 50 to 75 pounds, which the crew can manage, but the suit is also pressurized, stiff and bulky. Bending at the waist takes effort. Reaching overhead is awkward. Working in the suit for an 8-hour surface excursion is exhausting. Astronauts on Apollo missions reported severe fatigue after just a few hours of moonwalks. Mars missions plan for routine 8-hour excursions, repeated almost daily. After 500 days of this, the crew's muscles have been pushed in ways no Earth astronaut has experienced, while still missing the load they need to fully recover. Their bones are thinner. Their hearts are smaller. Their balance is off. Then the launch window opens. Time to climb into the ascent vehicle, accept 3 Gs of acceleration, and hope the body holds together long enough to make orbit. If the body doesn't hold, there isn't a second chance. And if the body does hold, the dust they breathed for 500 days is still in their lungs. Martian dust is not like Earth dust. It is finer than talcum powder, sharper than sand, and laced with toxic chemicals that no Earth environment has prepared the human body to handle. Every step the crew takes on the surface kicks it up. Every spacesuit they wear collects it. Every airlock cycle drags it inside the habitat. The dust is the silent threat that no Mars mission has fully solved. Start with the size. Martian dust particles are smaller than 4 micrometers across, on average. Some are smaller than 1 micrometer. For comparison, the smoke from a wildfire contains particles around 0.4 to 2.5 micrometers. The dust on Mars is in the same range as the most dangerous airborne pollutants on Earth. It penetrates deep into lungs, lodges in alveoli, and stays. Then there's the chemistry. Mars' surface soil contains perchlorate salts, sometimes at concentrations of 1% by weight. Perchlorates disrupt thyroid function in humans. They also act as oxidizers, meaning they react aggressively with organic compounds. In the lungs, perchlorates can cause inflammation, scarring, and potentially long-term damage. Astronauts inhaling Martian dust over 500 days are running an experiment that has never been performed. The Apollo program offered a small preview. Lunar dust was a known problem. After moonwalks, the astronauts brought dust back into the lunar module on their suits. Inside the cabin, the dust released a smell described as burnt gunpowder. Crews developed eye irritation, sneezing, and respiratory complaints. The dust clung to everything and resisted cleaning. Mars dust will be worse. Apollo missions lasted days. Mars missions last over a year on the surface. The dust accumulation in the habitat over that time frame is a chronic exposure problem. Beyond human health, the dust threatens equipment. It coats solar panels, reducing power output. NASA's Spirit and Opportunity rovers eventually died, partly because dust accumulation on their solar arrays cut their power below survival thresholds. Dust gets into bearings, joints, and seals. It scratches faceplates. It shorts out electronics. Spacesuit seals are especially vulnerable. The fine particles work into the metal-on-metal joints of the suit's hard upper torso, slowly grinding them. Over hundreds of cycles, suits that worked perfectly on day 1 start leaking. A leaking suit on Mars is a fatal emergency. Mission planners have proposed solutions. Suit ports, where the suit attaches to the outside of the airlock and the crew climbs in from inside the habitat, keeping dust outside. Magnetic dust removal systems. Dedicated dust airlocks with high-pressure cleaning. None of these has been tested in actual Martian conditions for a full mission duration. The dust also carries a static electric charge. Mars's thin atmosphere and dry conditions create strong electrostatic forces. Dust particles cling to surfaces with a force that wet rags cannot remove. Cleaning becomes a constant, exhausting task. Every spare moment in the habitat is spent fighting dust that cannot be fully removed. Dust storms are another factor. Mars has planet-wide dust storms that can last for months. During a major storm, visibility drops to near zero, solar power collapses, and the crew is sealed in their habitat with limited external operations. The 2018 global dust storm killed the Opportunity rover. A crew during such a storm faces extended power rationing, limited communications, and the psychological strain of being trapped indoors for weeks. After 500 days of breathing this dust, what condition the crew's lungs are in is anyone's guess. There is no autopsy data, there is no clinical baseline, and the dust is just one threat. The same star that powers the dust storms also throws other things at the crew, on a timeline nobody can predict. The star at the centre of our solar system is not quiet. It throws out streams of charged particles continuously, in what scientists call the solar wind. Most of the time these particles are mild, and Earth's magnetic field deflects them harmlessly. But every few weeks the star erupts. A coronal mass ejection blasts billions of tons of plasma into space at speeds up to 4 million miles per hour. When that plasma hits a spacecraft, the radiation dose can spike from background levels to lethal in hours. A Mars crew, travelling for 6 to 9 months in deep space, has no magnetic field protecting them. They are flying through whatever the star throws at them. The biggest solar storm ever recorded happened in 1859. Known as the Carrington event, it sent a massive coronal mass ejection toward Earth. Telegraph systems across North America and Europe failed. Sparks flew from telegraph keys. Auroras were visible as far south as the Caribbean. If a storm of that size hit a Mars-bound spacecraft today, the radiation dose to the crew in unshielded spaces could exceed 5,000 millisieverts in a single event. That dose is acutely lethal. The crew would experience radiation sickness within hours and die within weeks. Mission planners build storm shelters into spacecraft for exactly this reason. The crew has minutes of warning when a major event is detected on the star. They scramble to a small, heavily shielded area, often the cabin's central tunnel surrounded by water tanks, food supplies and equipment. Inside the shelter, the dose during a major storm drops dramatically, perhaps to a few hundred millisieverts. A few hundred millisieverts is survivable. It is also enough to cause immediate radiation sickness, nausea, vomiting, fatigue, and a measurable hit to the immune system. The crew rides out the storm sealed in a coffin-sized chamber, sometimes for hours, sometimes for days. Predicting these storms is imperfect. The star's surface shows precursors like sunspot growth and magnetic field disturbances that mission planners watch closely. But the actual eruption can happen with little warning, and the particles travel fast. By the time the warning reaches the spacecraft, the crew may have only 15 to 30 minutes to reach the shelter. In zero gravity, moving fast is harder than it looks. Crew members have to grab handholds, push off walls, navigate cabin geometry without floating into corners. Practicing storm drills is part of every long-duration mission. But when the alarm goes off for real, in the middle of a sleep cycle or during a meal, the response time is everything. There's a worse scenario. What if the storm hits during a critical mission phase, like the descent into Mars's atmosphere, when the crew is strapped into seats and cannot move, or during the ascent off Mars on the return leg? In those moments, the crew has no way to reach the shelter. They absorb the full dose. Mission timelines try to schedule transits during periods of lower solar activity. The star has an 11-year cycle, with peaks and quiet periods. Choosing a launch during the quiet phase reduces but does not eliminate the risk. Even in quiet periods, major storms can occur. The crew that arrives at Mars has likely experienced at least one significant solar event during transit. Their cumulative radiation dose is higher than predicted models said it should be. Their immune systems are slightly weakened. And their psychological state has been tested by the experience of huddling in a shelter, knowing the next few hours decide whether they survive. Then they have to get out, set up base, and stay sane for 500 more days. 3 years. That is how long the first Mars crew will be away from Earth on a minimum energy mission. 3 years of confined spaces, the same 5 faces, recycled air, freeze-dried food, and the slow accumulation of every small irritation that comes with extreme isolation. No human has ever done this. The closest analogues are Antarctic winter over cruise, submarine deployments, and the Miranus long-duration missions. None of them last as long as a Mars trip. None of them are as far from rescue. The psychological strain on Mars crews is something every mission planner studies and few discuss publicly. The reason is simple. The data is alarming. NASA and international space agencies have run analogue missions to study isolation effects. The Mars 500 experiment, conducted in Russia from 2010 to 2011, sealed 6 men in a mock spacecraft for 520 days. They simulated the trip to Mars, a surface excursion, and the return. The crew was carefully selected, professionally trained, and monitored constantly. By the end of the mission, 4 of the 6 crew members had developed measurable behavioural or psychological problems. Sleep disturbances were widespread. 2 crew members became withdrawn and stopped engaging with the team. 1 developed clinical depression symptoms. Performance on cognitive tests declined for most of the crew over time. This was on Earth, with doctors available. With the option to abort, real Mars crews will not have those safety nets. Communication delays of up to 24 minutes one way mean a crisis on Mars cannot be resolved by talking to Earth in real time. A crew member experiencing a breakdown is dependent on the 4 or 5 people around them, the same people they have been locked with for over a year. The other crew members are also stressed, exhausted, and not trained as full mental health professionals. Interpersonal conflict is the most studied risk. In Antarctic stations, where crews winter over for months in isolation, fights are common. Some are minor. Some end in physical violence. In one documented case, a crew member at the Soviet Vostok station attacked a colleague with an ice axe during a chess dispute. The mission was completed only because a relief flight could land in spring. On Mars, no relief flight is coming. Crew dynamics on long missions follow predictable patterns. The first weeks are characterized by excitement and cooperation. The middle phase, sometimes called the third quarter phenomenon, sees morale drop sharply. Small disagreements escalate, subgroups form. By the time the crew is preparing to leave Mars, they may not be on speaking terms. Sleep is another casualty. The Martian soul is 24 hours and 39 minutes long. That extra 39 minutes shifts the crew's circadian rhythm forward every day. Over weeks, their internal clocks drift completely out of sync with any standard schedule. Researchers studying analog Mars missions report chronic sleep deprivation, mood disorders, and cognitive impairment as a direct result. There's also the simple fact of being far from Earth. Astronauts on the International Space Station can look out the window and see the planet they came from. Mars crews lose that view. Earth becomes a bright dot. By the time they reach Mars, Earth is just another star. The crew is genuinely, physically alone in a way no humans have ever experienced. If a crew member breaks down badly, the options are limited. Sedation, restraint, isolation in a section of the habitat. None of these are good outcomes, and all of them take resources away from the rest of the mission. The crew that lands on Mars has already been through the worst of the transit. The crew that survives 500 days on the surface has been through worse. The crew that has to launch and fly home has been through everything together, and during all of that, the very signal connecting them to Earth has been getting slower. Light travels at about 186,000 miles per second. On any normal day, that speed feels infinite. Press send on a message, and it arrives instantly. Make a phone call, and the voice on the other end answers without a pause. We live our entire lives inside a bubble where information moves faster than we can perceive. That bubble pops the moment a spacecraft leaves Earth orbit. The distance between Earth and Mars varies enormously depending on where the planets are in their orbits. At their closest, they sit about 34 million miles apart. At their farthest, when the star is between them, they are over 250 million miles apart. A radio signal travelling at light speed takes between 3 and 22 minutes to cross that gap. One way. A round-trip conversation where Mars sends a message and Earth responds can take up to 44 minutes from question to answer. This is not a small inconvenience. It is a complete redefinition of what it means to be in contact with home. The crew cannot have a real conversation with anyone on Earth. Every exchange becomes a series of recorded messages. Hello, how are you? Here is what happened today. Here is what we did. Here is what worried us. Send. Wait. 20 minutes pass. The response comes back. The crew has already moved on to other tasks. They listen to the response, record their own, send it. The cycle repeats. For routine operations, this is workable. Mission control plans days in advance. Crews work from procedures uploaded the previous Earth day. Decisions are made on Mars time, with Earth providing guidance hours later if needed. For emergencies, the delay is catastrophic. Imagine a fire breaks out in the habitat. The crew has minutes to control it. Mission control on Earth, watching telemetry, sees the fire alarm trigger 22 minutes after it actually starts. By the time controllers respond, advise, and send their guidance, another 22 minutes have passed. The crew has been fighting the fire alone for 44 minutes before any Earth-based input arrives. The fire is either out or has killed them. Every emergency on Mars is local. The crew handles it without help. They know this before they leave. They train for it. But knowing it intellectually and living it are different. There is a deeper problem. Humans are not designed for isolation from their species. Every astronaut who has flown to space has reported moments of intense longing for home. On the International Space Station, crews can call family members, see their faces, talk in real time. The connection is degraded but present. On Mars, the connection breaks down to text and recordings. A child saying goodnight to a parent on Mars sends a message and waits half an hour for the goodnight back. By then, the child is asleep. Holidays, birthdays, anniversaries, deaths in the family, all of these arrive as recorded news. The crew member learns about a parent's funeral 22 minutes after it happens. They cannot call, they cannot fly home. They send a message into the void and wait for the next one. The psychological toll of this asynchronous existence is hard to measure in advance. Astronauts on longest missions report increased loneliness over time, even with daily real-time contact. Mars crews lose that real-time contact entirely. Some studies suggest the disconnection from Earth could become its own form of trauma over a multi-year mission. There's also a practical problem for mission operations. The crew has to be more autonomous than any space crew in history. They cannot wait for Earth to solve problems. They have to diagnose, plan, and act independently, then report results. Which means when the time comes to fire up the ascent vehicle and leave Mars, they are doing it largely alone. The rocket they need to climb into has been sitting on the surface for 2 years, and nobody on Earth is sure it still works. Every Mars mission profile that includes a return depends on a single piece of hardware. The Mars Ascent Vehicle, or MAV, it is the rocket that launches the crew off the surface of Mars and into orbit, where they rendezvous with the larger spacecraft that brings them home. The MAV is the linchpin. If it works, the crew might come back. If it doesn't, they are stuck on Mars forever. There is no rescue mission within reach. What makes the MAV uniquely difficult is where it lives. It is not assembled in a factory and rolled to a launch pad on Cape Canaveral. It is built somewhere on Earth, packed inside a lander, flown 140 million miles across space, dropped through Mars's thin atmosphere, and parked on the surface. There it sits, exposed to dust, temperature swings of 150 degrees, occasional micrometeorite impacts, and the slow degradation of every seal and electronic component. It sits there for 2 years before the crew needs it. Then, after sitting through 700 days of Martian conditions, it has to ignite, generate full thrust, and lift the crew to orbit. First try. If anything has gone wrong during those 700 days, the crew dies trying to launch. Compare this to launches on Earth. A rocket on a launch pad in Florida is monitored every minute. Engineers can roll it back, repair it, swap components, retest systems. A rocket on Mars is alone. Whatever fails, fails permanently. The crew has limited tools and limited training to repair complex propulsion systems. The MAV has to be small. Every kilogram of rocket landed on Mars cost roughly 10 kilograms of fuel and structure during the launch from Earth. Mission planners pare the MAV down to bare essentials. A small ascent capsule for the crew. Fuel tanks. Engines. Guidance and control. Nothing extra. Most MAV designs propose 2-stage rockets. The first stage burns until it is empty, then drops away. The second stage, smaller, finishes the climb to orbit. 2-stage designs are mass efficient, but they double the number of critical events that have to work perfectly. Engine ignitions, separation events, fuel transfers, control sequences. Each is a single point of failure. NASA's Mars Sample Return mission, currently in development, includes a small MAV designed to launch sample tubes back to Mars orbit. That MAV, if it ever flies, will be the first rocket to launch from another planet. It carries no humans. It carries about 600 grams of Martian rocks. The mission has already been delayed by years due to budget overruns and engineering difficulties. The crewed version, scaled up to lift 4 humans, is orders of magnitude more complex. The fuel itself is the other gamble. The MAV launches using methane and oxygen, ideally produced on Mars by the Sabatier reactor and water extraction systems described earlier. If those systems fail to produce enough fuel, the MAV cannot launch with full tanks. A partial fuel launch leaves the crew short of orbital velocity. They climb part of the way and fall back to the surface. Or they reach a low orbit and cannot rendezvous with the return spacecraft. There are no half-success outcomes for the MAV. Either the crew makes it to orbit, or they don't. NASA's risk assessments for crewed Mars missions identify the MAV launch as the single highest risk event in the entire profile. Higher than landing, higher than transit, higher than any other moment. And the MAV has never been built, not even a prototype. Every design exists on paper or in computer models. No one has ever ignited a rocket on another planet's surface. The first time it happens, 4 lives depend on it. Building a rocket is hard. Building a rocket that can survive being shipped to another planet, sit in Martian conditions for 2 years, and then ignite perfectly is something humanity has never attempted. The reason is simple. Testing it requires Mars. Earth-based testing can simulate parts of the Martian environment. Vacuum chambers can reproduce the low atmospheric pressure. Refrigeration can drop temperatures to -80 degrees Fahrenheit. Dust chambers can throw fine particles at hardware. But no Earth facility can simulate all of these conditions simultaneously for 2 years with the additional factors of partial gravity, cosmic radiation, and the unique atmospheric chemistry of Mars. So engineers test components, not whole systems. An engine in a vacuum chamber, a fuel tank under pressure cycling, a guidance computer in radiation simulation. Each component passes its own tests in its own conditions for limited durations. Then everything gets assembled, packed into a lander, and shipped to Mars on the assumption that the components will work together for 700 days in conditions no Earth lab can fully replicate. The track record on this assumption is uneven. NASA's Mars rovers, much simpler than a crewed ascent vehicle, have suffered numerous failures during their missions. The Spirit rover got stuck in soft soil and could not move again. The Opportunity rover died in a dust storm. The Curiosity rover has had wheel damage, computer failures, and drilling system problems. Every Mars surface mission encounters issues that ground tests did not predict. A MAV has to do something none of those rovers do. it has to ignite a chemical rocket engine after sitting on the surface for 2 years. The engines have moving parts, including turbopumps, valves, and combustion chambers. Each of these can degrade in dusty, low-pressure, thermally cycling environments. Valves are especially vulnerable. The valves in a rocket engine have to open and close precisely under high pressure to control fuel and oxidizer flow. A valve that has sat unused for 2 years, exposed to Mars conditions, may not seal properly when it tries to operate. A leaking valve during ignition can cause an explosion. A stuck valve can prevent ignition entirely. Turbopumps are worse. These are spinning machines that pressurize fuel before it enters the combustion chamber. They run at tens of thousands of revolutions per minute, with bearings that need lubrication and tight tolerances. After 2 years of thermal cycles and dust exposure, the bearings may have lost their lubrication. The first time the turbopump tries to spin up, it could seize. There is no way to test these systems on Mars before the crew uses them. Some mission concepts include a brief test fire of the engines, perhaps a 1-second ignition, weeks before the planned launch. If the test fails, the crew has weeks to maybe figure out what went wrong with limited tools. They do not have replacement parts. They do not have a second MAV waiting nearby. There is one rocket, and it has to work. Mission planners try to mitigate this with redundancy. Backup valves, redundant turbopumps, multiple ignition systems. Each layer of redundancy adds mass, and mass on Mars is brutally expensive. There is a hard limit to how much redundancy a MAV can carry, while still being light enough to land. The result is a piece of hardware whose failure modes are partially understood, partially predicted, and partially unknown. The first crewed launch from Mars will reveal the truth. The crew will not know whether the MAV works until they are strapped in, the engines are firing, and the ground is dropping away. By then, the only options are success or death, and one bad seal on the way home decides which it is. In aerospace engineering, a single-point failure is a component whose failure causes the entire system to fail. Engineers spend their careers trying to eliminate single-point failures, building redundancy into every system. On Earth, this works reasonably well. Backup pumps, backup computers, backup parachutes. If one fails, another takes over. On Mars, redundancy has a weight cost that the mission cannot fully absorb. So single-point failures remain, and on Mars, every single point failure is potentially fatal. Consider a few examples. The valve that controls oxygen flow into the habitat. If it sticks closed, the crew suffocates within hours. If it sticks open, oxygen vents into the atmosphere and is lost. The valve has redundant designs, but the wiring or the actuator that drives it might not be redundant. One bad part, one bad solder joint, one corroded contact, and the system fails. Or the seal on the airlock between the habitat and outside. The seal flexes every time the airlock cycles, hundreds of times over the mission. Over 500 days, fatigue accumulates. Dust gets into the seal. If the seal develops a slow leak, atmosphere bleeds out faster than the life support system can replace it. The crew either fixes the seal or runs out of breathable air. Or the heat exchanger in the propellant production plant. This is the component that transfers heat from the Sabatier reactor to the surrounding cooling system. If it clogs, the reactor overheats and shuts down. The crew loses fuel production for as long as it takes to repair. If it cannot be repaired, the fuel never gets made, and the crew cannot launch home. These are not rare failures. On the International Space Station, components fail constantly. Pumps, sensors, computers, valves. The crew is trained to swap out failed parts, often several times a week. The station has an extensive supply of spare parts, regularly delivered by cargo missions. Every failed component can be replaced. On Mars, supply runs are impossible during the mission. The crew has only what they brought with them, and what was pre-positioned by earlier robotic landers. If a critical part fails and no replacement exists in the inventory, The crew has to either improvise a fix or accept the loss. NASA has studied the problem of mission-ending failures. Internal risk assessments for crewed Mars missions estimate that the probability of at least one critical failure during the round trip is significant, possibly above 50%. Most of these failures could be managed with some loss of capability. A few of them would be unrecoverable. The unrecoverable failures cluster around a small number of systems. Life support, propellant production, the MAV itself. Loss of any of these means loss of crew, with no realistic chance of rescue. Some mission concepts try to address this with redundant infrastructure on the surface. 2 habitats instead of 1, in case one becomes uninhabitable. 2 propellant production plants. 2 MAVs. The cost is enormous. Each duplication adds tens or hundreds of tons to the launch mass, requiring additional rockets, additional landings, additional everything. SpaceX's plan calls for multiple starships landing at the same site, providing some natural redundancy. NASA's plans typically include only one of each critical system due to budget constraints. The cost of redundancy on Mars is the cost of survival. Cutting redundancy saves money, but it raises the probability that one bad valve, one bad seal, one bad weld ends the mission. The first crew to Mars will be flying with less redundancy than any human spaceflight in history. They will be flying farther from rescue than any humans have ever flown, and the budget that determines what they bring with them is finite. Which is exactly why mission planners keep coming back to the same uncomfortable solution. The numbers are brutal, and the numbers are public. NASA's internal estimates for a crewed Mars mission, including the round-trip return, range from 500 billions to $1 trillion, depending on the mission profile and timeline. SpaceX has not published cost estimates for a crewed Mars mission, but independent analyses suggest figures in similar ranges, even with the company's lower launch costs. Compare this to Apollo, which cost about $283 billion in 2025 dollars. A Mars mission costs 3 to 10 times more, and Apollo's longest mission was 12 days. A Mars mission is over 1,000 days. The cost is driven by mass. Every kilogram launched from Earth costs money, and a Mars mission requires hundreds of tons of equipment, fuel, supplies, and habitats to be delivered to Mars over multiple launches. The infrastructure alone, before the crew even leaves Earth, requires dozens of heavy-lift rocket launches. Each launch costs hundreds of millions to billions of dollars. Now consider what the return trip adds. The MAV, the propellant production plant, the fuel storage tanks, the Earth return vehicle waiting in Mars orbit, the heat shields and parachutes for Earth re-entry, the recovery operations. All of this is dedicated to bringing the crew home, and it represents the largest single cost component of any crewed Mars mission. Mission analyses consistently show that a one-way mission where the crew lands on Mars and stays costs roughly 1/3 of a round-trip mission. The savings come from eliminating the MAV, the return propellant production, the Earth return vehicle, and all associated systems. The mass savings cascade backward through the launch architecture, reducing the number of rockets needed and the total fuel required. For mission planners trying to get a crewed Mars program funded, this equation is hard to ignore. Cut the round trip, fund 3 one-way missions instead, send 3 times as many crews. The math favours the one-way option ruthlessly. There's a deeper economic problem. A round-trip Mars mission delivers crews back to Earth after 3 years. What did they accomplish during those 3 years? Some scientific work, some samples, some experience for the next mission. The return crew is exhausted, deconditioned, and unable to fly again for years. The investment per scientific outcome is enormous. A one-way mission, by contrast, leaves a crew on Mars permanently. They continue to work for years, decades potentially. They build infrastructure, conduct ongoing research, and prepare the way for additional crews. The scientific output, per dollar spent, is much higher. This is the cold logic that has shifted Mars mission planning over the past 2 decades. The Mars One project, announced in 2012, was explicitly built around one-way missions for cost reasons. Robert Zubrin's Mars Direct allowed for return but accepted high risk. Elon Musk's Starship plan technically includes return capability, but the long-term vision is colonization, with crews staying indefinitely. Government space agencies like NASA still officially plan for round-trip missions. The political optics of leaving astronauts on Mars permanently are difficult, but the budget pressures year after year push the agency towards smaller missions, longer surface stays, and incremental approaches that look more like one-way colonization than traditional exploration. There's also the recovery cost. Bringing a crew home means recovering them from a capsule splashdown or land landing, providing months of medical rehabilitation, and potentially treating long-term health issues from radiation, bone loss, and other mission impacts. The medical costs alone can run into hundreds of millions of dollars per crew member. Skip the return, and these costs vanish. The first humans on Mars will not be staying because they want to. They will be staying because the math made the decision for them. And the man who first ran that math, decades ago, designed the only mission plan that pretends to bring them home. Robert Zubrin is an aerospace engineer who spent the 1990s arguing that everybody else was overcomplicating Mars. NASA's plans at the time, sometimes called the 90-day study, involved giant orbital assembly facilities, lunar staging bases, and price tags over $400 billion. Zubrin, working at Lockheed Martin, looked at the plans and saw waste. He proposed something simpler: Mars Direct. The idea was elegant. Send a robotic lander to Mars first, 2 years before any humans. The lander carries a small nuclear reactor, an empty fuel tank, and a chemical processing plant. The plant uses Martian carbon dioxide and hydrogen brought from Earth to manufacture methane and oxygen. By the time the crew launches, the lander has filled the fuel tank, and a fueled MAV is waiting on the surface. Then send the crew. 4 astronauts in a small habitat, launched directly to Mars without orbital assembly. They land near the pre-positioned MAV. They live on the surface for 500 days. They use the MAV to launch back to orbit, where they rendezvous with a return vehicle that takes them home. The whole mission, Zubrin argued, could be done with existing rocket technology for around $20 billion. NASA's official planners called the number absurd. Zubrin called the official plans absurd. History sided partially with both. The mission profile Zubrin designed has been adopted, in modified forms, by every serious Mars architecture since. Pre-positioning fuel infrastructure, using Martian resources, accepting long surface stays. These are now standard. But the price tag turned out to be much higher than Zubrin estimated, because every component required more development than initial plans assumed. Mars Direct also accepted a level of risk that NASA found politically unacceptable. The mission relied on the propellant production plant working perfectly, with no human there to fix it during the 2 years it operated. If the plant failed, the crew would arrive with no fuel for return. Zubrin's response was that they could still do useful science on the surface, and later missions could rescue them. Rescue from Mars is essentially fictional. A rescue mission requires its own launch window, its own transit time, and its own MAV. By the time a rescue mission could arrive, the original crew would have run out of supplies and died. Zubrin acknowledged this implicitly. The risk was the cost of doing the mission at all. Mars Direct also accepted the radiation problem with similar matter-of-factness. The transit habitat had basic shielding, mostly food and water tanks arranged around the crew quarters. The dose was higher than NASA's career limits. Zubrin argued the limits were too conservative and should be reconsidered for exploration missions. The crew selection criteria reflected the risk profile. Zubrin proposed older astronauts, perhaps in their 50s, who had completed their childbearing years and accepted the elevated cancer risk. Younger astronauts had more years for cancers to develop and were less acceptable for the mission. These positions were controversial and remain so. but they were honest. Zubrin was explicit that a Mars mission required accepting risks that previous American spaceflight had refused to accept. The alternative, in his view, was never going to Mars at all. NASA studied Mars Direct extensively. The agency adopted many of Zubrin's ideas, but always layered additional safety margins on top, increasing mass and cost back toward the levels Zubrin had been trying to escape. The Design Reference Architecture series of NASA Mars plans bears the structural fingerprints of Mars Direct, with all the cost increases that come from making it safer. Zubrin himself, now in his 70s, continues to advocate for Mars missions. He is one of the most vocal critics of overly cautious Mars planning. He has also said publicly that he would volunteer for a one-way mission if NASA would let him. Mars Direct accepted the possibility that crews might not come home. The plans that followed it have quietly inherited that acceptance, even when the mission profiles claim otherwise. Buzz Aldrin walked on the Moon in 1969. He was the second human to step onto another world. After Apollo, he became one of the most persistent advocates for human Mars exploration, and he spent decades developing his own mission architecture. The Aldrin Cycler. The concept is ingenious. Instead of building a single spacecraft that flies to Mars and back, Aldrin proposed building a permanent transportation system. A large spacecraft, called a cycler, follows a special orbit that takes it past Earth and Mars repeatedly, indefinitely. The cycler never stops at either planet. It flies a fixed loop through the solar system, swinging by Earth every 26 months, then swinging by Mars, then back to Earth. The crew launches from Earth on a small taxi vehicle, rendezvous with the cycler as it passes by, and rides the cycler to Mars. As the cycler approaches Mars, the crew transfers to another small taxi vehicle and descends to the surface. The cycler continues on its loop, eventually returning to Earth. When the crew is ready to come home, they launch from Mars on another taxi, catch a returning cycler, and ride it back to Earth. The advantage is that the cycler itself, once placed in its orbit, never needs to slow down or speed up. It coasts on gravity. The fuel cost of moving large amounts of equipment, supplies, and habitat space between Earth and Mars drops dramatically. Crews ride a kind of celestial bus, while only the small taxis need significant propulsion. Aldrin's specific cycler design uses a 30-month round-trip period. A crew that catches the cycler at Earth flies to Mars, lands, stays on Mars, and then catches the next cycler home. The total mission time, including the surface stay, is about 30 months. This is longer than minimum energy direct missions, which can complete the round trip in 21 months on the most aggressive profiles. The trade-off is that cycler missions are theoretically much cheaper to operate, because the same large spacecraft serves multiple missions. There are problems. The cycler concept requires a permanent fleet of cycling spacecraft which has to be built, launched into the cycling orbit, and maintained. The initial construction cost is enormous. The orbit is also slightly unstable, requiring small periodic corrections to maintain, which means the cyclers need their own propellant supplies even though they don't decelerate at planetary encounters. The biggest problem is the encounter velocity. When a cycler passes Earth or Mars, it is moving fast relative to the planet. The taxi vehicles that rendezvous with the cycler have to match its speed, which requires significant fuel. At Mars in particular, the encounter velocity is high, around 8 kilometers per second. Slowing a crew taxi to match the cycler's speed, then later launching a returning crew up to match the next cycler's speed, requires substantial propellant. Aldrin has continued promoting the cycler concept for decades. He has worked with universities and aerospace firms on detailed designs. Purdue University has a centre named after him that studies cycler trajectories. The concept remains technically sound but financially unfunded. NASA has studied cyclers as part of its Mars planning. The agency has not adopted them, primarily because cyclers require committing to multiple missions over decades, and political support for long-term programs is unreliable. The cycler concept does not solve the core problem of Mars return. It still requires crews to launch off Mars on a MAV, still depends on propellant production, and all the other technologies discussed in this script. The Cycler simply makes the long-distance transport cheaper once everything else works. Aldrin, like Zubrin, has been clear that early Mars missions will involve risk. He has not made the same explicit statement about one-way missions, but he has acknowledged that the first crews will face dangers far beyond what previous astronauts have accepted. The Cycler is one piece of an answer. It does not change the underlying physics that traps crews on Mars for hundreds of days. It just makes the long ride between planets a bit more affordable. NASA's official Mars mission architecture is called Design Reference Architecture 5.0, or DRA 5.0. It was published in 2009 and represents the most comprehensive plan the agency has produced for sending humans to Mars. The plan is over 800 pages long. It covers every aspect of a crewed mission, from launch from Earth to return splashdown on Earth. The mission profile is staggering. Total mission duration is 1,100 days, that is over 3 years. Crew size is 6. Mass delivered to the Martian surface is approximately 100 metric tons. Number of heavy lift launches required from Earth is at least 7, possibly more. Total mission cost, depending on assumptions, ranges from $500 billion to over $1 trillion. The plan includes round-trip return for the crew. It also acknowledges in technical language that the return is the hardest and riskiest part of the mission. DRA 5.0 breaks the mission into 4 major phases. First, pre-deployment of cargo and infrastructure to Mars, including the propellant production plant, surface habitats and the MAV. This phase takes place over the launch windows preceding the crew's departure, which means as much as 4 years before the crew launches. The cargo is sent on slower trajectories to save fuel. Second, the crew transit to Mars. This phase lasts about 6 months, on a fast trajectory that minimizes radiation exposure and time in zero gravity. The crew rides in a transit habitat with limited shielding, accepting radiation doses that exceed current career limits. Third, the surface stay. The crew spends 500 days on Mars, conducting science, maintaining equipment, and waiting for the launch window to open for return. During this phase, the propellant production plant continues to manufacture fuel, the crew makes excursions in pressurized rovers, and they live in habitats designed to provide some radiation shielding. Fourth, the return transit. The crew launches on the MAV, rendezvous with a return vehicle in Mars orbit, and flies back to Earth on another 6-month trajectory. They re-enter Earth's atmosphere, splash down in the ocean, and are recovered. Throughout the document, NASA acknowledges enormous uncertainties. The propellant production plant has never been built at the size required. The MAV has never been tested. Radiation shielding for the transit and surface stays is acknowledged to be inadequate for current career dose limits. The crew's physical condition after 1,100 days is acknowledged to be unknown. The plan includes risk mitigation strategies, but most of them depend on technologies that are still in development. Improved radiation shielding requires new materials. Better life support requires more reliable hardware. Faster propulsion would help shorten the trip, but no faster propulsion is currently available. NASA's own risk assessment in DRA 5.0 estimates the probability of loss of crew at somewhere between 10 and 30% for the full mission. Different parts of the mission have different probabilities. The transit phases are relatively safe, with most risk coming from radiation events. The landing on Mars is risky but manageable. The surface stay is dangerous from accumulated wear on hardware. The MAV launch is the single most dangerous event in the mission. DRA 5.0 has been updated periodically since 2009, but the fundamental architecture has not changed dramatically. Subsequent NASA planning documents have explored variations, alternatives, and improvements. None of them have eliminated the core challenges. None of them have produced a Mars mission profile that is significantly cheaper, safer, or shorter than DRA 5.0. The plan exists. It is technically feasible. It has not been funded. Every American president since 1989 has announced some version of a Mars program. None of these announcements have led to actual budget allocations sufficient to execute DRA 5.0, or any similar plan. The mission keeps being designed, refined and shelved. If Draft 5.0 ever flies, it will be the most ambitious crewed mission in human history. It will also accept that some crew members may not come home. The plan does not say this in plain language, but the math says it clearly, and there are already plans that don't even pretend to bring them home. In 2013, an American businessman named Dennis Tito announced a plan to send a married couple on a flyby of Mars. The mission was called Inspiration Mars. Tito was a former NASA engineer who had become a multi-millionaire and was the first paying space tourist, having visited the International Space Station in 2001. He proposed using his own money, plus other private funding, to launch the first crewed Mars mission. The plan was bold and stripped down. A small spacecraft with 2 crew members would launch in January 2018 on a free return trajectory. The trajectory would take them past Mars, swinging close enough to the planet for spectacular views, and then bring them back to Earth using gravity alone. No landing, no surface stay, no propellant production. The mission would last 501 days, end to end. Tito chose a married couple specifically. He believed 2 crew members in an existing relationship would be psychologically more stable than a randomly assigned pair. The cabin would be tiny, perhaps 600 cubic feet, about the size of a small van interior. The crew would have minimal privacy, recycled air, basic food, and almost no exercise capability. They would never get out of their seats for over a year and a half. The mission profile required launching in January 2018, when planetary alignment was particularly favourable for a free return trajectory. The next similar window would not occur until 2021, and then not again for over a decade. The mission ran into problems quickly. The funding never materialised at the levels needed. The propulsion system the plan depended on, an upgraded version of NASA's Space Launch System, was not going to be ready by 2018. The radiation exposure during the 501-day flight, travelling deeper into space than any humans have ever flown, was assessed to be likely lethal, even with shielding. The radiation problem was the killer. Inspiration Mars studied multiple shielding options. They proposed lining the spacecraft walls with water tanks and food supplies, providing about 5 grams per square centimetre of mass shielding. Even with this, the crew would receive an estimated 600 to 700 millisieverts of radiation over the flight, slightly below career limits but uncomfortably close. A major solar event during the flight could push the dose much higher, into immediately dangerous territory. Some NASA radiation specialists who reviewed the plan called it unsurvivable in the worst case. Tito's team disagreed, but acknowledged the risk was real. The mission was quietly abandoned. Tito's organisation continued to explore variations, including a 2021 launch with a different trajectory, but no version ever attracted enough funding to proceed. What Inspiration Mars represented, however, was a clear shift in how Mars missions could be conceived. The plan deliberately avoided the hardest parts of a Mars mission. No landing, no surface stay, no fuel production, no MAV. By stripping away these elements, Inspiration Mars cut the cost and risk dramatically. They also accepted that the mission would not actually visit Mars in any meaningful sense. The crew would see Mars through a window for a few hours and then fly home. This kind of compromise has informed later mission concepts. Some current planners argue that a crewed Mars flyby should be the first crewed mission to Mars, not a landing. The argument is that flying past Mars is much easier than landing on it, and that the experience would advance the program toward eventual landing missions. Critics argue that a flyby mission accomplishes little beyond demonstration, and that the scientific value is far below the cost. Inspiration Mars was the first serious attempt to imagine a crewed Mars mission that was not hopelessly expensive. It failed, but its assumptions, particularly about radiation and minimum mission duration, have shaped every plan that followed. The plan also indirectly highlighted something else. If a flyby mission was going to be too dangerous, what did that say about full landing missions, which involve much longer exposures and far more complex hardware. The next plan that came along answered the question by simply removing the return trip altogether. In 2012, a Dutch entrepreneur named Bas Lansdorp announced a plan that broke from every previous Mars mission concept. Mars 1 would send 4 people to Mars in 2023, with no return trip. Ever. The crew would live on Mars permanently. New crews would be sent every 2 years to expand the colony. The whole project would be funded partly by selling broadcast rights to a reality TV show following the astronaut selection and mission. The plan was ambitious. The plan was also, in many ways, fraudulent. Mars 1 claimed it could establish a Martian colony by 2023 for about $6 billion. Mission planners with experience in real space programs, when reviewing the technical details, found the plan's assumptions to be impossible. The propulsion systems Mars 1 depended on did not exist at the scales needed. The life support technologies they proposed had not been demonstrated in space. The funding model, based on television broadcast rights, was wildly speculative. Lansdorp was not an aerospace engineer. He was an entrepreneur with a background in business and energy. The technical advisors he attracted included some legitimate scientists, but the overall plan was widely criticised as unrealistic. NASA called the timeline impossible. Aerospace experts pointed out that no rocket existed that could deliver Mars 1's stated payloads. SpaceX, whose rockets Mars 1 sometimes referenced as a possible launch provider, never had any formal involvement. Despite these problems, Mars 1 attracted enormous public attention. The application process for astronaut candidates received over 200,000 applicants. The reality TV component drew media coverage worldwide. Books were written, documentaries were filmed. The application process itself revealed something interesting about human nature. People were lining up to volunteer for a mission with no return. Not just hundreds or thousands, but over 200,000 people willing to leave Earth permanently. Mars 1 eventually narrowed the candidate pool to 100 finalists, then to a smaller group from which the first crews would have been drawn. None of the selections were ever flown. Mars 1 declared bankruptcy in 2019. The company's claims about funding, technology, and timelines turned out to be largely fabrications. The founder denied wrongdoing, but the project's collapse was complete. The reality TV show never materialized. No astronauts were trained, no hardware was built. What Mars 1 did, however, was plant a seed, the idea that the first humans on Mars might never come home, and that this was acceptable, even desirable, entered public consciousness in a way it had not before. Subsequent discussions of Mars exploration began including one-way scenarios as a serious option, not just a dystopian thought experiment. SpaceX's approach, while officially preserving the option of return, has consistently emphasized colonization over exploration. Elon Musk has spoken openly about wanting to die on Mars. The implicit assumption in Starship's mission profile is that early crews will stay, with return capability developing over time as infrastructure grows. NASA, more cautiously, has begun including extended surface stays in its planning, with options for crews to stay through multiple launch windows, effectively turning short missions into multi-year deployments. The line between exploration and colonization has blurred. The Mars 1 bankruptcy did not kill the one-way idea, it just discredited a particular implementation. The underlying logic that one-way missions are cheaper, lighter, and possibly more survivable than round-trip missions remains compelling. Future plans that take this logic seriously will likely succeed where Mars 1 failed, by being technically realistic about what one-way colonization actually requires. What Mars 1 demonstrated, beyond doubt, was that humans were willing to volunteer. The supply of people who would leave Earth forever was not the limiting factor. The limiting factor was, and remains, the technology to keep them alive once they got there. And that technology bends every economic argument toward the same conclusion. Mission planners, when they run the numbers honestly, keep finding the same answer. A one-way mission to Mars is not just cheaper than a round trip, it is also, in several important ways, safer. The math runs through mass. Every kilogram delivered to the Martian surface costs roughly 10 kilograms of launch mass on Earth. A round-trip mission has to deliver the crew, their habitat, supplies for the surface stay, and all the systems needed to bring them home. Those return systems include the MAV, fuel for the MAV, the propellant production plant, fuel storage, the Earth return vehicle in Mars orbit, and the heat shield and parachutes for Earth re-entry. Together, these return systems weigh tens of tons. Strip them out, and the mass that has to be launched from Earth drops by perhaps 50% or more. Fewer rocket launches, less fuel, lower costs. The savings cascade through every part of the mission architecture. Now look at the safety side. A round-trip mission has to succeed at every phase of the mission, including the most dangerous phases on the return leg. The MAV launch from Mars, the transit back to Earth, the re-entry into Earth's atmosphere. Each of these adds risk. Each of these has been identified by NASA as a potential mission-ending failure point. A one-way mission eliminates all of these risks. The crew lands on Mars and never has to launch again. They never have to fly back to Earth in zero gravity. They never have to survive re-entry forces with bones weakened by years of low gravity. The most dangerous phases of the round-trip mission simply don't exist. There is also the question of what the crew can survive psychologically. A round-trip mission requires the crew to maintain functional performance through the entire 1,100-day mission, including the return leg. They have to be capable of operating the MAV, conducting orbital rendezvous, managing the return transit, and surviving Earth re-entry. If their psychological condition deteriorates significantly during the mission, the return becomes impossible. A one-way mission allows for more flexibility. If a crew member breaks down, the rest of the crew can absorb the loss. There is no critical event that requires everyone to perform at peak capacity. The crew can adjust, accommodate, and continue. The mission's success criteria are different. Habitat design is also simpler. A round-trip habitat has to be self-contained, with redundant systems for surface operations and the return spacecraft. A one-way habitat can be expanded over time, with new modules delivered by subsequent missions. The crew can build infrastructure that grows year by year, rather than living in a sealed capsule designed to launch back to Earth. Some mission concepts now propose what they call permanently planted missions. The crew lands and immediately commits to staying. Over time, additional landings deliver more crew members, more equipment, and more supplies. The colony grows incrementally. Eventually, return capability might become possible, but only after years of development. Critics of one-way missions raise legitimate concerns. The crew has no escape if the colony fails. Resupply becomes essential, since the crew cannot survive indefinitely on the supplies they bring. Medical emergencies are managed locally, with no possibility of evacuation to Earth. Death on Mars becomes a routine reality, with crew members aging, getting sick, and dying without ever returning home. These criticisms are valid. They describe the trade-off, not a fatal flaw. The trade-off is that the mission becomes possible at all. Round-trip missions with their full mass and risk loads have been studied for 60 years and never funded. One-way missions, with their lower costs and risks, may be the only versions that ever fly. The first crews on Mars are likely to be the first permanent residents. They will not be there as explorers waiting to return home. They will be there as colonists, making Mars their home, because the math has decided for them. And the math has not gone unnoticed by the volunteers. When Mars One opened its application process in 2013, the assumption was that finding volunteers for a one-way Mars mission would be the hardest part. Who would actually leave Earth permanently, knowing they would never see their families again, never feel ocean waves, never breathe outdoor air on a summer afternoon? The answer, as it turned out, was over 200,000 people. The numbers shocked even Mars One's organisers. The application process required candidates to submit videos, complete questionnaires, and pay a small registration fee. Despite these barriers, applications poured in from every continent. Doctors, teachers, engineers, students, retirees. Married couples applied together, asking to be sent as units. Parents applied, accepting that they would never see their children grow up. The motivations varied. Some applicants spoke about adventure, the chance to be part of human history, to be remembered as the first Martians. Others spoke about scientific contribution, about the chance to do work that no one else could do. Others, more honestly, spoke about wanting to escape Earth, for reasons that ranged from personal struggles to political disillusionment to simple boredom. What the applications revealed was that the supply of willing volunteers far exceeded any realistic mission's crew slots. Even after accounting for medical, psychological and skill-based screening, the number of qualified candidates was orders of magnitude greater than any planned mission needed. This pattern has repeated. SpaceX has not formally opened a recruitment process for Mars crews, but Elon Musk has publicly stated that the company has more interested volunteers than it could ever fly. NASA's astronaut selection processes consistently receive thousands of applications for a handful of slots. When the agency announced its Artemis mission program in 2017, over 18,000 people applied to become astronauts. The number for an actual Mars program would likely be far higher. Studies of volunteer populations have tried to understand who these people are. Demographics span all age groups, all educational backgrounds, all economic levels. There is no single profile of the Mars volunteer. What unites them is a willingness to accept terms that most humans would find unacceptable. Some psychologists have called this self-selection process the most important factor in eventual Mars colonization. The crews will not be reluctant draftees. They will be people who specifically wanted to go, with full understanding of the risks. This selection bias may help with the psychological challenges of long-duration missions, since volunteers who chose this path are more likely to stay committed when conditions deteriorate. Other psychologists are more skeptical. They point out that a desire to leave Earth sustained over years of waiting may be different from the lived experience of actually living on Mars. Volunteers who imagine themselves as Martian pioneers may discover, after months of dust, dim red sunlight and recycled food, that they wanted something different from what Mars actually provides. By the time they realize this, they cannot leave. The legal frameworks for Mars colonization are unclear. Existing space law is built on the Outer Space Treaty of 1967, which prohibits national appropriation of celestial bodies but says little about the rights of individual settlers. Mars colonists may exist in a legal grey zone, neither citizens of any Earth nation in any practical sense, nor full subjects of any new Martian government. Their rights, their property, their relationships, all of these become questions without clear answers. Mars One's volunteer pool, despite the project's eventual failure, demonstrated something important. The bottleneck for Mars colonization is not human willingness, it is engineering. The technologies to keep humans alive on Mars, particularly through the long surface stays and the dangerous transits, do not yet exist at the reliability needed. But the people, the crews willing to fly, are already lining up. Over 200,000 of them, ready to leave Earth and never look back. There is one scenario in which a Mars crew could eventually return home, even if they were originally sent on a one-way mission. The crew, working on the surface for years, could build the return vehicle themselves, using Martian resources and equipment delivered by subsequent missions. This scenario is currently impossible. Building a rocket capable of launching humans off Mars and into orbit requires an industrial base that does not exist anywhere in the solar system except on Earth. Steel mills, foundries, machine shops, chemical plants, electronics manufacturing. Each of these represents decades of accumulated technology, supported by global supply chains and tens of millions of workers. A Mars colony of even a few dozen people cannot replicate this infrastructure. They can perform basic operations like 3D printing parts from delivered materials, mining and processing some local resources, and assembling components shipped from Earth. They cannot manufacture rocket-grade engines, complex avionics, or the specialized alloys needed for high-performance aerospace applications. Those things require an industrial civilization, not a research outpost. So a Mars colony in the early decades depends on Earth for its hardware. Earth ships rockets, components and supplies. The colony assembles, deploys and uses what Earth sends. The colony does not build its own return capability from scratch. This means the crew's return possibility depends entirely on Earth's continued willingness to send return hardware. If political support shifts, if budgets get cut, if other priorities emerge, the colony loses its return option. The crew that thought they might come home eventually finds themselves, after years of waiting, without the hardware they were promised. There is a deeper problem. Even if Earth ships return hardware regularly, building a complete return mission requires more than just the MAV. It requires the propellant production plant, fuel storage, the Earth return vehicle in Mars orbit, the re-entry capsule, parachutes, recovery systems. Every one of these has to be functional at the same time, on a coordinated timeline, with no critical failures. Mars colonists trying to return after years on the surface would face all the same problems early Mars missions face, plus additional problems unique to their situation. Their bodies would be more deconditioned than first mission crews. Their equipment would be older and more worn. Their hardware would have been assembled in less controlled conditions than Earth-based manufacturing. Each of these factors increases the probability of failure. Some long-term plans, including some SpaceX concepts, propose a gradual industrial build-up on Mars. Year by year, decade by decade, the colony develops its own manufacturing capability. Eventually, after generations, Mars might have a complete industrial base capable of building its own rockets. The first humans on Mars would not see that day. They would die long before Mars achieved industrial independence. The timeline for such a build-up is debated, but no serious estimate puts it at less than several centuries. SpaceX has spoken about cities on Mars within decades, but the technical reality is that supporting such cities requires sustained Earth resupply for the foreseeable future. Self-sufficiency is a long-term goal, not a near-term plan. For the first crew, this means their return depends entirely on Earth. They cannot help themselves. They cannot accelerate the timeline. They wait for hardware that may or may not come, on a schedule they cannot control, while their bodies break down and their resources slowly deplete. This is the unstated premise of Mars colonization. The first colonists are not building a foundation for their own return. They are building a foundation for someone else's return, perhaps generations later. Their bones will stay on Mars. Their work will benefit those who come after them. Their journey ends where they land. It is a kind of contract that humans have made before, with the West, with the New World, with frontiers in every era. The first generation pays the price, so the second generation can enjoy the benefits. Mars is just the latest version of this old story, on a new and unforgiving world. Some long-term thinkers about Mars envision a different future. Rather than humans living forever in sealed habitats, breathing recycled air through filters, they propose terraforming Mars, changing the planet itself to make it more Earth-like. A breathable atmosphere, liquid water on the surface, agriculture in open fields, eventually people walking outside without spacesuits. The idea is captivating. It is also, on any realistic timeline, far beyond the lifespans of the first colonists. Terraforming Mars would require fundamentally restructuring the planet's atmosphere, hydrology, and surface chemistry. Mars currently has an atmosphere that is 1% the density of Earth's, mostly carbon dioxide. Surface temperatures average negative 80 degrees Fahrenheit. Liquid water cannot exist on the surface for any sustained period. To change this, terraformers would need to thicken the atmosphere, raise the temperature, and provide the planet with a magnetic field strong enough to protect the new atmosphere from solar wind erosion. Each of these steps is enormously challenging. Thickening the atmosphere requires releasing massive amounts of greenhouse gases. Mars has frozen carbon dioxide in its polar caps and absorbed in its regolith. Some terraforming proposals involve heating the polar caps to release the carbon dioxide, thickening the atmosphere over centuries. The amount of energy required is staggering. NASA studies suggest that even with optimal release of all available carbon dioxide on Mars, the atmosphere would only reach about 7% of Earth's density, still too thin for humans to breathe without pressure suits. Raising the temperature is another long process. Greenhouse warming from the released carbon dioxide would help, but additional heating would be needed. Some proposals involve giant orbital mirrors focusing sunlight on the polar caps. Others suggest spreading dark dust across the surface to absorb more radiation. Each option requires building space infrastructure on a scale that does not currently exist. The magnetic field problem is the worst. Mars lost its magnetic field billions of years ago when its core cooled. Without that field, solar wind strips away the atmosphere over time. Any new atmosphere terraformers create would slowly erode back into space unless protected. Some proposals involve placing a satellite at the Mars-Sun Lagrange point, generating an artificial magnetic field that shields Mars from solar wind. The technology to do this exists in theory, has not been built at any scale, and would be a permanent infrastructure investment. Realistic terraforming timelines run from centuries to millennia. Optimistic estimates suggest 200 years to make Mars marginally more habitable, with breathable air requiring perhaps 1,000 years or more. Pessimistic estimates suggest terraforming may not be achievable at all with technologies we can currently envision. For the first humans on Mars, terraforming is irrelevant to their personal experience. They will live their entire Mars lives in pressurized habitats, going outside only in suits, eating food grown in sealed greenhouses. The dream of walking on a green Martian surface is for descendants who may not yet exist. There is a darker consideration. Some terraforming proposals are ethically debated. Mars may have once had life. Some scientists argue it may still have microbial life, hidden in subsurface aquifers or ice deposits. Terraforming the planet would fundamentally alter or destroy these potential ecosystems. Mars colonists face a choice between making the planet more useful for human habitation or preserving it as it is, possibly with ancient life forms still hidden in its rocks. The terraforming timeline does one important thing for the present mission. It establishes that Mars colonization is a multi-generation project, not a single mission effort. The first crews are the first chapter in a story that may take centuries to fully unfold. They will not see the end of that story. They will only see the beginning. Their job is to survive long enough to write the first paragraph. A Martian, in the science fiction sense, is an inhabitant of Mars. In the literal sense, a Martian is a person whose body has adapted to Mars conditions, whose social structures have formed on Mars, whose identity is shaped by the red planet. The first humans who land on Mars and stay become Martians by physics, not by choice. The transformation begins immediately. The first day on Mars, the crew breathes recycled air, drinks water from local sources, eats food grown in Mars greenhouses or shipped from Earth. Their bodies start adjusting to 38% gravity. Their skin begins to react to the radiation that penetrates the habitat. Their internal clocks shift to the slightly longer Martian day. Over weeks and months, the changes accelerate. Bone density continues to decline, even with exercise. Muscles atrophy. The cardiovascular system adapts to lower gravity loads. The crew's bodies become Mars-conditioned, optimized for an environment that no Earth human has ever lived in long-term. If the crew stays on Mars for years, the changes become permanent. By the time they have lived on Mars for 5 years, returning to Earth gravity would be physically impossible. Their bones would shatter under their own weight. Their hearts could not pump strongly enough to maintain blood pressure. They would be unable to walk, possibly unable to stand. Earth, the planet they came from, would have become inhospitable to them. This is not a metaphor. This is medical reality. Some studies of long-duration spaceflights suggest that astronauts who spend more than 2 years in altered gravity experience permanent musculoskeletal changes. Mars colonists who stay for a decade or more may simply never be able to live on Earth again, even if a return mission could somehow bring them back. The first humans on Mars become Martians the moment they land. Every day they stay, they become more Martian and less terrestrial. The line is gradual, but the destination is clear. There are also psychological changes. Long isolated populations develop different social norms, different vocabularies, different ways of relating to each other and to the world. The first Mars crew, isolated from Earth for years, will develop their own microculture. Their children, if they have children on Mars, will be raised in this microculture. By the third generation, Mars residents will have lived their entire lives in a Mars-shaped reality. Earth will be a distant origin, half remembered through stories and old recordings. Reproduction on Mars is its own enormous question. No human pregnancy has ever occurred in altered gravity. The effects of pregnancy, fetal development, and birth in 38% gravity are completely unknown. Some studies of mammals in microgravity have shown disrupted fetal development. Whether viable Mars pregnancies are possible at all is an open question. If they are possible, the children born on Mars will be the first true Martians. Their bodies will form under Mars gravity, with Mars radiation as a constant input, surrounded by Mars conditions from the moment of conception. They will be biologically different from their Earth-born parents. Their children, in turn, may be different again. Within a few generations, if the colony survives, Mars residents may be a distinct population in any meaningful biological and cultural sense. They will share ancestors with Earth humans, but live different lives, shaped by different physics. The first humans on Mars are not just colonists. They are the founders of a new branch of the human story. This is what the math of Mars missions has been pushing toward all along. The first crew goes, knowing they are unlikely to return. They become Martians. They build the place where future Martians will be born. The story of Mars is not the story of explorers visiting a strange land and coming home. It is the story of a new world being populated, slowly, painfully, irreversibly, by people who will never come back. There is a final question that mission planners, when they are honest, eventually ask themselves. If the first crew to Mars is going to die there, what is the point? The question has multiple answers depending on whose perspective you take. For the crew themselves, the answer is usually personal. They wanted to go. They knew the risks. They believed the mission mattered enough to give their lives for. This is the same answer that explorers have given throughout human history. From the first humans who left Africa to the early polar explorers to the Apollo astronauts who knew their odds were not great. Some humans have always been willing to walk into one-way journeys, for reasons that are theirs alone. For science, the answer is concrete. Mars holds answers to questions that cannot be answered from Earth. Whether life ever existed on Mars. Whether life could exist there now, in subsurface aquifers. What the early solar system was like. How planetary atmospheres evolve and decay. How human bodies and minds respond to long-duration alien environments. The first crew would generate scientific knowledge worth more than any uncrewed mission could provide. For technology, the answer is incremental. The technologies developed for Mars missions advance every related field. Better life support systems for terrestrial applications. Improved medical monitoring for chronic conditions. New manufacturing techniques for autonomous remote operations. Each technology returns benefits to Earth long after the original mission ends. For humanity as a species, the answer is harder to articulate but perhaps the most important. Establishing a presence on a second planet, even a small and struggling one, changes our species' position in the universe. We become a multi-planet species. If something happens to Earth, a major asteroid impact, a global war, an engineered pathogen, the Mars colony provides a backup. Even if the colony is small and dependent on Earth in the short term, the fact of its existence changes the long-term odds of human survival. This last argument is the one that animates many of the people pushing hardest for Mars missions. Elon Musk has spoken openly about wanting humanity to be a multi-planet species as insurance against extinction events. The argument is that even if the first crews die on Mars, even if many subsequent crews die, the eventual establishment of a self-sustaining colony justifies the cost. The argument is also controversial. Critics point out that the resources spent on Mars colonization could solve enormous problems on Earth, from poverty to climate change to disease. The opportunity cost is real. Every $1 billion spent on Mars is $1 billion not spent on Earth-based priorities. Defenders of Mars exploration respond that human civilization has always pursued multiple priorities at once, and that scientific and exploratory work has consistently generated benefits beyond what the planners imagined. The wealth and capability that allows Mars exploration also allows other priorities to be addressed. The two are not zero-sum. The first humans on Mars will live, work and die under this argument. They will be the first generation of Martians. Their bones will rest in Martian soil, mineralizing slowly under conditions Earth biology has never experienced. Their names will be remembered, perhaps for as long as humanity itself remembers anything. Their descendants, if they have descendants, may eventually look back at the first crews the way we now look back at the early humans who crossed land bridges into unknown continents. Brave, foolish, lucky, doomed. All of these things at once. People who went forward into the unknown because going forward was somehow what humans do. The mission planners who designed the Mars architecture, who calculated the fuel budgets, who chose which compromises to accept, understood from the beginning that the first crew would probably not come home. They wrote it into the math, they wrote it into the schedules, they wrote it into the radiation tables and the bone density curves. The first humans on Mars will never return home because home is a place they leave when they board the rocket. By the time they reach Mars, they are no longer Earth's people. They are Mars's people now, and Mars, the cold red planet that has waited billions of years for visitors, will keep them. The journey ends where it began with this fact. The math said no, humans went anyway. And from that going, a new world begins.